In this video, we will explore bond line structures and functional groups. In general chemistry, we like to use Lewis structures to depict molecules. However, as you will see in organic chemistry, the molecules get more complicated and much more bigger, so much so that Lewis structures become cumbersome. To go around this, organic chemists have come up with some shorthand ways to depict molecules. We'll explore a couple of these in this lesson.
So for example, a 3-carbon chain known as propanol can be depicted in this Lewis structure, but it could also be written in a condensed form. In the condensed form, the hydrogens connected to a carbon are grouped together. So for example, on the far left here, you have 3 hydrogens connected to the same carbon, so we can abbreviate that as CH3. And the middle 2 carbons have 2 hydrogens hanging off of them, so we can abbreviate them as CH2s. So in the condensed structure, you would write CH3, CH2, CH2OH. So this condensed formula is good to a certain extent. Once your molecule gets a lot bigger, for example, this molecule, or you need to be able to see special features of that molecule rather quickly, the condensed formula will also not be sufficient. So instead, we will rely on something called the bond line structure. The bond line structure, also sometimes called the line structure, or sometimes called the skeletal structure. So for example, propanol can be drawn like so. So what are the features of this bond line structure? One feature is the zigzag lines. The ends of each line represents a carbon. So for example, here we have this line. It's 1. So there's a carbon at one end and a carbon at the other end. The second line going down, again, at the ends of that line are 2 carbons. The one that we already highlighted and another one there. However, if that line ends up connecting to an atom that is not carbon or hydrogen, then it would be indicated. And in this case, you're connected to an oxygen. So we have 3 carbons in total. So again, the ends of each line segment would represent a carbon, unless otherwise indicated. Also on a bond line structure, hydrogens that are connected to carbon can be ignored and are assumed to be present. And this is why it's good to know the patterns of bonding in organic chemistry. Remember we said that carbon is tetravalent? That means it has 4 bonds, right? If we take a look at this first carbon here, it's already connected to 1 carbon, so it must be connected to 3 other bonds. So if nothing is drawn in, then you can assume that those 3 other bonds are 2 hydrogens. So that means that that carbon is connected to 3 hydrogens, right? Whereas the carbon in the center is connected to 2 carbons, so 2 bonds. So that means it has 2 more bonds left to be tetravalent. We assume then that those 2 bonds are to 2 individual hydrogens. Also note that lone pairs don't have to be drawn. So in our example on oxygen, there should be 2 lone pairs, but we don't have to draw it explicitly out in a bond line structure. And lastly, you want to explicitly write out the existence of all other atoms. So like nitrogen, oxygen, sulfur, chlorine, they all must be drawn out. There's a collective term for these types of atoms that are not hydrogens and carbon. They're called heteroatoms. So the best way to test that you fully understand bond line structures is to be able to count how many hydrogens there are in these structures. So let's do some examples. So in our first example here, first off, we've indicated 2 parallel lines. I forgot to mention that previously, but if you have 2 parallel lines, that means it is a double bond. So how many hydrogens are there? So remember, all these lines are bonds. So at the end of each bond is a carbon, unless otherwise indicated. So there's a carbon here, a carbon here, a carbon here, and a carbon here, okay? So let's figure out how many hydrogens are connected to each of these carbons. The first one, the red carbon, how many bonds is connected to it already? It's 1, 2, 3, 4, right? Since there's already 4 bonds connected to it, there are 0 hydrogens there. Next, the yellow one, how many bonds are connected to it? We have 1, 2, 3. So therefore, it has to have 1 more missing hydrogen. What about the green carbon? So it has 1, 2, 3 bonds again. So it has how many more hydrogens? 1 more hydrogen. And lastly, our blue carbon. It has 1 bond connected. So it must have 3 more hydrogens. So in this molecule, we have a total of 6 hydrogens. Let's do another example. Okay, here. How many hydrogens do you think is connected to that blue carbon? It has already 3 bonds, so it has 1 more hydrogen. Very good. What about this next carbon here? It has 2 bonds, so 2 more hydrogens. How about this carbon here? 2 bonds already, right? So 2 more hydrogens. How about this carbon? It has 3 bonds, so one more hydrogen. How about this carbon here? 2 bonds already, so 2 more hydrogens. Okay, this is something we haven't seen yet, right? This triple bond here. So how many bonds does this carbon already have? So the triple bond is 3 bonds and then another single bond, right? So that's 4 already, so it's already complete, so it has 0 hydrogens there. What about on the other end of that triple bond? It has 3 already, so that carbon needs 1 more bond. So that is the hydrogen. And so I just want to also point out that at this end over here, it is connected to a chlorine, so there are no hydrogens there either. All right, so how many hydrogens is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a total of 9 hydrogens. And so remember, lone pairs can be omitted sometimes. So for example, in this chlorine, you should really see 3 sets of lone pairs, whereas this oxygen is a divalent atom, so you should see 2 more sets of lone pairs. These lone pairs may or may not be omitted. It's good to remember the bonding pattern of different atoms. Let's go back and review the 3 main atoms you will see over and over again, which are carbons, nitrogens, and oxygen. Let's start first with carbon. Remember that we said carbon was tetravalent. So that means that carbon generally has 4 bonds. Well, it turns out that rule needs a little bit of a qualification. So in fact, it is only true that carbon will have 4 bonds if it was neutrally charged. There are carbons that are positively or negatively charged. So let's take a look at those cases. So here's an example of a positively charged carbon. Another name for this is a carbocation. Remember that the original number of valence electrons for carbon is 4. So in order to have a positive formal charge, the carbon must be missing an electron. Because it has only 3 valence electrons, it can only form 3 bonds. Because it's a carbocation, it only needs 3 bonds. And in this bond line drawing, it already has those 3 bonds. So we would assume that it has no hydrogens connected to it. Let's take a look at another example. Can you see how many hydrogens, if any, are connected to this positively charged carbon? It's a carbocation, so it needs 3 bonds. It already has 2 bonds, so the last undrawn bond must be to a hydrogen. Let's try that again. What if the carbocation was at the end of this bond line structure? So if it's the end carbon, it already has 1 bond, so how many more hydrogens are connected to it? You need 3 total, so therefore there are 2 hydrogens. So again, these are called carbocations. Now let's take a look at the opposite case. Instead of a positive charge, you can also have a negative charge. Negatively charged carbons are called carbanions, and they are a result when a carbon has 1 extra electrons than it should have, so a total of 5 valence electrons. Because of those 5 valence electrons, a carbanion will have 2 of those electrons be a lone pair and the other 3 to be in a bonded pair. So you will still have 3 bonds in a carbanion. So we see there's 1 bond to another carbon, so there must be 2 more hydrogens. Now let's go to nitrogen. Remember, nitrogen was a trivalent atom. So typically it would have 3 bonds. There would be 1 more lone pair on this nitrogen, but we don't have to draw it in, but you can if you want. Now, if that lone pair was used in a bonding situation, then that nitrogen would have less electron density. It would be positively charged. On the other hand, if a nitrogen has less bonds than it typically has, so it has more lone pairs, then it would be negatively charged. Let's see how well we understand this. What if I drew in this molecule here? Does this nitrogen have 1 set of lone pairs, 2 sets of lone pairs, or no lone pairs? Hopefully you recognize it has 1 set of lone pairs because it follows a regular bonding pattern for nitrogen. Being a trivalent, it already has 3 bonds. 1, 2, 3. So therefore, it has 1 set of lone pairs. So let's also revisit the same idea for oxygen. So oxygen is divalent, so you have 2 bonds to it, and also leaving behind 2 sets of lone pairs. But when you have less bonds than it usually has, that means it has a formal charge of -1. That means it gained another set of lone pairs. So in this case, it would have 3 sets of lone pairs. On the opposite case, if you see it having more bonds than it usually typically has of 2, then you know that it's going to be positively charged, and it would only have 1 set of lone pairs. We can practice with this in both ways. So in this first example here, let's see if we can draw in the lone pairs that are missing. Starting with the oxygen on the left-hand side, we see that it has 2 bonds already, which is a typical bonding pattern for oxygen. So typically then, how many lone pairs does it have? It would have 2 sets of lone pairs. What about the middle oxygen? So it has a formal +1 charge, which means it would have 1 set of lone pair. And lastly, the oxygen on the right, it has a -1 formal charge, so you would expect 3 lone pairs. So in our next example here, What if I give you all the lone pairs already drawn in? What is the formal charge of the heteroatom oxygen? So let's take a look at this one at a time. The one on the top left, it has 3 as your valence bond, so you automatically should think it is a formal charge of +1. On the bottom, lower right, then it has 2 as a valence bond, so it should have 0 formal charge. So you should go back and forth between these different annotations.
Now that we have bond line structures to help us analyze large and complex molecules, we should be able to recognize special features in a molecule. These special features will help us analyze the properties and the reactions of a molecule. These special features are known as functional groups.
Functional groups are structural units within organic compounds that are defined by specific bonding arrangements between specific atoms. It will be extremely important to be able to quickly recognize most of these functional groups because they are the key structural elements that define how organic molecules react. And as we go through this course, we will learn the chemistry of each of these functional groups. For now, let's just learn how to recognize them when a bond line structure is drawn. The first set I want to go over are the functional groups that only contain carbon and hydrogens. The first one is an alkane. An alkane is characterized by a single bond between a carbon and a carbon. For example, here we have is propane. Alkenes, on the other hand, would have a carbon-carbon double bond. Notice that when we drew in the double bond, carbon cannot accommodate more than 4 bonds. So if you add in an extra carbon-carbon bond, then something has to give, right? You have to take 1 hydrogen away from those 2 carbons. And so this pattern will continue. If you take, again, these 2 hydrogens away to make another bond between doubly bonded carbon, you would then get an alkyne, a carbon-carbon triple bond. So you can represent alkyne as 3 parallel lines. And remember, alkynes are sp hybridized, so they would be linear. So you want to draw that line straight and not as a zigzag coming out there. Some terminologies here. Notice that the alkanes, all the carbons are full of hydrogens, so they are saturated. You can't add any more hydrogens to them, which is why alkanes are considered saturated hydrocarbons. Hydrocarbon meaning it has hydrogen and carbon only. And then the alkenes and alkynes would be the unsaturated because they are not yet saturated, they're not full of hydrogens. You can add more hydrogens to those carbons. So you've seen this when you talk about like saturated versus unsaturated fats. Actually, there's another group of hydrocarbons. They are called the aromatics. One example is this here is benzene. Aromatic compounds contain 1 or more rings with pi electrons that are quote-unquote delocalized all the way around them. Aromaticity is quite a complicated concept, so we will devote a whole lecture on this later on. But for now, if you see a ring compound with alternating double bond, it is likely an aromatic functional group. And now we can start adding more heteroatoms into our functional groups here. If a carbon-containing compound is attached with any of the halogens, we can call them alkyl halide or haloalkanes. And we can abbreviate the halogens with an X. So that could be a chloride, a fluoride, a bromide, or an iodide. Now, instead of a halogen at the end, if it's connected to an OH, which is known as a hydroxyl, then this becomes the alcohol functional group. Now, if we replace that oxygen with a sulfur, we then have a thiol functional group. Okay, so going back to this alcohol group, instead of having a hydrogen at that end, it's connected to oxygen, we have more carbons connected to it. We then can call this an ether functional group. Same thing on the sulfur side. When it is not an SH, but a sulfur connected to another carbon chain, we can call that a sulfide functional group. And continuing with this trend, instead of connecting to an oxygen at the end there, we are connected to a nitrogen, then we have what is known as the amine. Unlike the oxygen, if the heteroatom is a nitrogen, whether that nitrogen is connected to hydrogens or connected to carbons, they are all called amines. We can differentiate them, however, by calling them primary amines, secondary amines, or tertiary amines. This next group of functional groups contain carbon-oxygen double bond. This is a special type of bond called the carbonyl. We will see this carbonyl motif over and over again in the following functional groups. The first one is known as a ketone, in which there is a carbon-oxygen double bond, and on that carbon, you have more carbons connected to it. And if you change that carbon out to be a hydrogen, you have a different functional group called the aldehyde. And if you take away that hydrogen and put in instead an OH group, a hydroxyl group, it would be known as a carboxylic acid. Now from this carboxylic acid, you can actually make a lot of other derivatives. So we call these next groups carboacid derivatives. For example, instead of an OH, you add an oxygen and an alkyl chain next to it. And in inorganic chemistry, we can represent an alkyl chain with the letter R. We have here then an ester. If we replace the OR group with a nitrogen-containing group, we have then an amide, or sometimes called amide. Or you replace the entire side by a chlorine, it would be known as an acid chloride. And lastly, if there are two carbonyls attached to the same oxygen, then it is called an acid anhydride. So that's a lot of functional groups, but for now, we just have to learn how to recognize them when we see a bond line structure.